All right. You're able to hear me, right? Okay, let's go into your chapter 3. Okay. Now, chapter 3, we start to look into work and energy. So we're going to convert the schematic diagram of previously in chapter 2, we looked at equation of motion, F equal to ma. We need two diagrams, free body diagram and kinematics diagrams. In here, we look at what happened to the force, work and energy. In this case, we look into work as a force, work as a principle of work and energy, and power in efficiency and conservation of energy. So in this chapter, you start to hear some repeated word, for example, power, energy, work, and so on, right? The chapter objective, you have three objective here. So we will use force, velocity, and displacement. We will use force, velocity, and displacement to find work and energy. Yeah? So pay attention to force, velocity, and displacement, which is your S or height and something. So force, velocity, displacement is the main parameter that we'll look into when we try to find what is the work done by that particular object. After that, we will look at conservation of energy at the later chapter or later session. First, we look at what is work, right? What is work? What is the definition of work? Right. So work can only exist when the particle move, right? When a particle move, then work is done, energy is dissipated, or energy is done on that object, or receive energy. All right. So again, we focus on three parameters when we talk about work. We talk about force, velocity, and displacement. Displacement means the change of position. Right? A force will do work when the particles have a displacement. Right? The work can only be done or calculated if the displacement is done in the direction of the force. Spend some time to read this statement. When we talk about when we talk about work, you involve force and displacement. And what is the relationship with the displacement with the force? The displacement must be in the direction of the force. Okay? For example, if you have particles within work in the pathway, this red arrow dot here is a particle moving in a path in this earth. And let's say you have a force acting on this object. Right? Before we move forward, now when we talk about, we focus on work. Work. Work is a product of force and displacement. Both force and displacement must be in the same direction. Yeah. You view force as a vector, displacement as a vector. These two vectors must be in the same direction. Must be in the same direction. Only work can be calculated, or only work is being done by the force in the direction of this, only done by the force. Okay, so we only can calculate work when the force and direction they are the same. They are the same direction. Okay, displacement and force they are in the same direction. Then only work can be done. So look at that this schematic diagram. We have particles move in the path line, and let's say there's a force acting on this object in this direction. Okay, And because of this force, these particles move from one location to another location. Okay, let's say because of this force, this particle move from original location to another location defined by R and R prime. We have two locations here, 1 and 2. When you have two different points, you have a displacement happening in the system. Okay, I do it slowly. R is the first position we lock on. R prime is the second position we lock on when the force acting on this object. And you know, R is a vector, R prime is a vector. So when you combine the vector together, you have a change of R from this point to this point. Here to here defined as dr, or the difference of your R or position, dr. Why the direction in this way? Because this is the direction of your particles and also completing the vector diagram. This is the final position. So to get to the final position, you need to have a start additional distance to reach the final. Okay, so we keep updating this schematic diagram. We have a particles and the force is acting on it in this direction. We have a change of direction over here defined by dr. From this diagram, this vector diagram here, you know that R prime is a resultant vector. So this one, R prime equal to R plus dr. So what is your dr? R prime equal to R plus dr. So you can write your dr equal to R prime minus R. Okay, this is a vector diagram. Yeah? This is a resultant. You can see this one as your resultant because this one is from beginning to the end. R prime equal to R plus dr. Put your term in dr. So dr equal to R prime minus R. Okay. Then we try to link what is ds. This is the path traveled by the particles. For example, this line is a path that we define as S that we learned in chapter 1 and chapter 2. We always use blue color to represent path. So the magnitude of dr, the magnitude of dr is a vector. Vector have magnitude and direction. So magnitude of dr is ds. So let's say in this diagram, we have a vector dr and the magnitude of dr is ds. Okay, so this is the just extra explanation. What is ds? Ds is this curved line here, very small curved line. Dr is a direct direction to the beginning, not beginning, from the one point to another point. Okay, make sure you understand the notation that we use here, yeah? And what is their relationship. Because we're going to build one equation from here to build the equation of, to derive the equation of the work here. So what we have here, a little bit different from the previous one. Now there's a force in red color appeared in the diagram. In chapter 1, we don't have force. Chapter 2 also, we don't have force in the pathway. Now, in chapter 3, there is an additional force acting on the object. Okay. Now, we start to look at one more parameter inside this diagram. If the angle between the tails of the R and F is theta, here, if from here, the tail of the R, this one, and F, you have a theta, like that. Work done by the force, again, work done by the force is a scalar quantity. You know that you have a scalar quantity and vector quantity, right? You know that when you learn about vector, you have a dot product and a cross product, right? So you have this equation. First equation for today, or for this session, du is a work. Work done by the force is the product of force multiplied by the displacement direction. Again, back to the definition of this statement. How work take place? When your force and displacement in the same direction. So when your force times the distance of the angle, cos angle, you create work. Look at this diagram. Force times ds. So how do you turn the component of ds align with the force? You split this vector into this one and this one. So, or you can use a trigonometry relationship. You see a triangular here. So we are using cos relationship to find the ds. All right. Or you can write, or you can convert the force align, or you can turn the force align with your ds. The important words here is the force and direction, the force and the displacement must be in the same direction. Then only work can happen. So this one give you this equation. Du equal to force ds cos theta is a scalar quantity. First equation for this chapter. Du equal to force ds cos theta. In this case, the force is not aligned with the displacement with the angle of theta. Then you use this equation. But this equation just tell you that one particular important principle we use here, force and displacement must be in the same direction. The product of these two will give you work. Okay, du equal to force ds cos theta. I move the equation on the, move up a little bit. This is the diagram that we developed just now. This is the equation that we come across. Work equal to force ds cos theta. Recall there is an appendix B. Dot product of two vector, it is a scalar. If you do not understand why dot product of two vector is a scalar, go ahead and refer to appendix B that I uploaded into the Teams folder under either lecture notes or tutorial. There's a one appendix B there. Under appendix B, under there are lots of things you read. One of the section it talk about vector. Okay. The one particular section you will see A dot B means vector A dot vector B, you get a scalar, you get AB cos theta. Okay. It is under vector chapter in mathematics. So here we can write our work equal force dot dr. Okay. This is the modification of equation. Okay. Modification using this concept over here. This is a vector. This is a vector. So AB cos theta. So ds cos theta is your dr. Okay, this one fall under vector mathematics chapter. Yeah? I just extract from the vector, I put it here. This is where you apply what you learned in the previous first 2 years of your degree. Right? So we transform this equation into this equation. It's a dot products. F dot dr, we get a scalar products. Okay. So this one you can interpret either you change your force direction aligned with the displacement, or you change the displacement aligned with the force. Both give you the same work value. Okay, still back to the definition of work. How you get work? When your force and displacement align same direction, you get work. Okay, displacement. Let's say your displacement going this way. As long as your force align with together in the same direction, these dot products will give you work. We use the U to use as a work. Remember, today you learn a new equation, U, capital U, to represent work. Later, you will see energy. Energy will use another symbol. When you see capital U, it means work. Okay, this is what I mentioned just now. Take note on that. We are using this schematic diagram to derive FDS theta. Take note now. What happens if you change your angle? When your angle is 0 to 90 degree, less than 90 degree, not equal to 90 degree. If the angle here is less than 90 degree, maybe 0 up to 98.99 degree. Because why? Cos 90 equal to what? 0. So when your force and displacement is 90 degree, you don't have work. Okay, so you try to imagine, this is your force, this is your displacement. If your force is 90 degree, they do not do work. But if your force slanted a little bit, they will do work because you can split your force to vertical and horizontal axis. So the maximum work done when the force align with your displacement. Okay. All right. Mean both lah. Mean both lah. Mean both. Force align with your displacement. This is displacement. When your force align with your displacement, they give you maximum force. Maximum work. Okay. Remember this statement, yeah. When your theta is from 0 and less than 90 degree, not 90 degree, then the force component and the displacement have some sense that work is positive. Meaning, if your angle is 0 to 90 degree, less than 90 degree, the work you done is positive. Meaning there is a positive work done. Okay? Take note. This start to give you the direction of the work. Whether when you get value of negative, what does it mean? When you get the value of positive, what does it mean? Okay, this one will lay the foundation of the calculation later. These slides will lay the fundamental understanding of your answer later on. Okay, so because in the exam of test later on, there will be particular section ask you to explain why you get negative, why you get positive for the work you done. You explain through this statement by back to the fundamental idea what is work. Okay, take note. This one will lay the foundation for the later topic that we will talk about. Try to remember that they have seen these slides before. Okay, you will answer some question like, hey, why this one positive, why that one negative? It's because of the angle, because of this cos theta equation here. Okay, so this one just opposite lah. If we have more than 90, it cannot be 90. Again, when in 90, cos 90 equal to 0, you have no work done. When this perpendicular, your force is perpendicular to your displacement, you get 0 work. All right. So when your angle is opposite, the angle is opposite means 90 to 180. See the marking sign here? You will get a negative work. Okay. Yeah, negative work. Meaning your force and displacement are not aligned. Okay. Another meaning also, why you get a positive value of work when your force and displacement, they are traveling or they are pointing to the same direction, then you get a positive work. When the displacement and work, they are opposite direction, you get a negative work. Okay, now try to remember that. It's important. Try to understand positive, negative means of your work. Work linked with force and displacement. Okay, right. Okay, so I already explained what happened when the force and displacement is 90 degree. This one is 0, so you don't have work. Another case where there's no work done is that the force is pinpoint to a fixed location. When the force is pointing to one location, let's say this force is pointing to one location and this location doesn't move. So when there's no movement, no displacement, no work. Okay. Now, what kind of question I can ask you from these two statements here? I give you a structure and I add in a force pointing to one of the screw there. One of the screw that go into the soil or go into the table. I ask you, what is the work done by that particular force? You explain using this equation, this statement. Okay? And the unit of your work is joule. Your unit of your work is joule. Joule equal to Newton meter. Where you get Newton meter? Force is Newton. Displacement is in meter. So Newton meter. Okay? Force is in Newton. Displacement is meter. Unit is Newton meter. Combination of Newton meter, you get joule. In the exam, when I ask you about work, your unit, you can either write in joule or you wrote in Newton meter. Okay? But most probably when I ask you about work, I will expect answer in joule. Okay? But sometimes The question will give you Joule. You convert Joule, find the force or find the displacement. Okay, so this is the conversion of information. Yeah, write somewhere in your notes. Yeah, because in tutorial I don't have this one pointing to this information. Okay, so we have done with the introduction of work under the effect of force and displacement. Okay, so from the previous 3 slides just now, when you want to find work, you look for 2 good friends, force and displacement. Okay, so you're talking about work, force, and displacement. So anyone missing, you can find another 2. Huh? Let me go for a few more slides. So what happened? Okay, if you have a single force, in this case, what happened? You have a variable force. Mean by you have that object was acting by a loss of force. Right? In this case, is these slides will show you variable force. What happened if yeah?
Just a few seconds on the previous slide.
Okay. Yeah. Go ahead. What is your question? What is your question just now?
I'm
What?
just writing down something.
Okay. So what is your question? What is your question?
No, I'm right. I was writing down something. I'm done. Thank you.
Oh, okay. Okay. All right. Oh, okay. I thought you have question to ask. All right. Okay. So I'm showing you a new diagram here. Previous slides, we only have one force. Now what happened? You have more than one force. Same diagram, but now I add one more forces. Okay, one more forces. All right. So what else? Sometimes I skip my slides. Okay, so this is just tell you what happened to the work lah. So this is not 2 force lah, but one force that you align this force to this S direction. Okay, then this one will not generate any work because it's already been projected to align with your displacement. So when you project this one go into here, this one will dismiss from the diagram. So the one that create work is this one that align to the displacement. Here we just add 2 more parameter. We call it S1 and S2. Okay. So you use integration to solve the work. So for example, the object work from this point to this point. How you modify from the previous equation, you write u 1 to 2 because this one is du. You integrate, you get u. Right? Integrate f dr from r1 to r2. So this is r1, r2. Okay. So how do you get this one? The previous one is du. Du means small changes of work. Du equal to f dr. Now, if you look at this equation, you have d something equal to d something. The next steps from this equation is always integration. Okay, you integrate this side, you get u. Integrate this side, you look for r. That's why you get this equation. U equal to 1 to 2 means position 1 to 2 equal to integration of r1, r2 force dot dr. This is the equation when you have a traveling particles along the path and you want to find what is the work done by this particle from this position to this position. You use integration. Okay, you pull the equation just now, you substitute back the dr equation, dr equal to ds cos theta. So you change the equation from force cos theta ds. Now once you change your ds, what you do to the limit here, you also change to ds. So I think this one should be changing to ds. So what can you link with this equation and the graph? So if you plot graph cos theta, cos f cos theta, and this one is s, okay, s, meaning the force that you change your angle, you align your force according to the direction of your displacement. That is the definition of work, because once your force and displacement are aligned together, same direction, you generate force. So the component that generate work is force cos theta and the ds here. So when you plot the graph of force cos theta versus s, you get a curvature graph here, right? Curvature graph here. And this is your S1, this is your S2. Okay. Again, I think I have some typo error here. It should be S, because I'm integrating with S. Typo error on my limit here. When I change my dr integration to ds, this one is not r, it should be s. S1 to S2. Take note, typo error on my slides. Okay, so basically what is this? If you look at this diagram, it's basically area under the graph of the curve of your graph. Okay. Next, we look at work of the constant force moving along a straight line. So this is work. The force is acting on the pathway, that curvature. That's why you have a curvature line here. What happens if your force is acting along straight line? Okay. What happens if your force is acting to the straight line? No longer curvilinear, but it's a linear line. So when your force is when your particles move along straight line, acting by the force of this force, and this force is having an angle difference from the reference line of the pathway here with the theta. So again, back to the definition of work. How work produced? When the force and the displacement go together, they produce work. So you need to change this force to two dimensions. One is this way, one is this way. And you know that when the force is perpendicular, there's no work done. So when you split this force into two components, one is here, one is here, by using trigonometry equation. So this component is F cos theta. This component here, when you split the force, is F sin theta. So F sin theta do not do work, although there's a force going up. But the going up perpendicular force do not create work, because F cos 90 ds, you get 0. Okay, so that's why there's no arrow pointing here. Although you can put arrow there, it doesn't help you in calculation the work, right? Okay, just remember that. In solving question in engineering dynamics, sometimes there's a reason you need to draw the vector there, the component there. In this one, I will remove the y-axis because I want to emphasize how work is done. But when you draw free body diagram later on for question, you still need to draw the vertical axis. Just let you know. Okay, because some of you might ask, what happened to the vertical axis force? It's still there, but it doesn't help in generating work. It's still there, but in terms of work, it doesn't do anything. Okay, so you get the force in cos direction, and you have a displacement from here to here. So basically, the total work done by the particle from S1 to S2 equal U1 from 1 to 2 equal F cos theta multiplied by the change of this distance. You take S2 minus S1. It's also, if you plot in the graph, if the particles or the object were in the move in the straight line, you will have a flat surface over here. This is the fixed force component, right? If the object move in a straight line, the force component acting along the flat surface always same. If you have a flat surface, and the force component always same at the angle of theta, then the force that contribute to the work is F cos theta multiplied by the change of displacement here, you get work. The area under the graph of F cos theta versus S is work. Okay, but anyway, for info, this module, we don't use this graph to derive equation, right? Because there are other tasks you need to do. Okay, you only see this graph when you do static or dynamic or static question. Okay, when you're doing the static module, then this graph is important. But since we are doing dynamic, this graph is just an explanation for you to understand. Okay. So this is what I explained just now. All right. I think you can understand what is this diagram transformed to mathematical model. Basically, you take F cos theta multiplied by the change of position. This equation works in the flat line. Okay, so there are two types of equation here. When your object moves in the curvilinear motion or a path or not straight line, you use this equation. When your object moves in the curvilinear motion, you use this equation. Again, typo error here. It should be S, not R. Right, typo error in my slides. If the object moves in straight line, you can use this equation. Straight away, F cos theta S2 minus S1. Again, this one is the component that go along your displacement, yeah? When you talk about work. Okay. Next, we have done with the force. Next, we move on to weight. What happened if you had a weight? Okay, what happened if you had a weight acting on the body? Does the weight done work or not? Okay, ask yourself a question. Does the weight done work or not? If the object, if the gravity pull the weight down, does it done work? Okay, go back to the definition of work. What I mean by work? If there is a force acting on along with the displacement, then work happen. Weight is one kind of force, right? So I just simply, this one look complex, but actually you just need to remember when there's a force going along with the displacement, there's a work done. So you look at this diagram, this one is in three-dimensional cases where you have X, Y, and Z axis. And this object here move from point 1 to point 2 in a pathway. This pathway is not a straight line. in a pathway in the blue color, and we focus on point 1 and point 2. This one before and after, or point 1 and point 2. And the weight is acting on, the gravitational force is acting on this object all the time. The weight always pointing down in y direction. Your dr is aligned with the path direction. Okay, R2, R1, R2. This is your dr. Okay. So now we start to use your vector or three-dimensional identity. Your dr in the three-dimensional dimension, your dr is a vector. Vector has magnitude and direction. Dr equal to magnitude in x and the x direction I plus y component plus z component. Okay, dr is a vector. Vector have direction, have magnitude and direction. So magnitude in x, magnitude in x, direction x. So direction x is I. Y magnitude, j is y direction. Vector j direction, y direction. Magnitude in z, and this one is z direction. Okay. But anyway, this axis can be tilted and can change. But what is important here is that once you are given a three-dimensional, you have to know that the change of r here, the r, you can write in a three-dimensional format with I, j, and k. Your w also can write in the vector form. W is the vector going down. Also have magnitude and direction. Magnitude is positive. Why there's a negative in front? Negative is because of the direction of your force going down. Because positive direction always going up. All right, is normally acceptable by all the scientists and mathematics around the world. All the direction going up is positive. So your gravitational force always pulling down. So that's why you get negative Wj. Okay. By combining these two. Okay. Again, what is work? Work is force multiplied by displacement. Both must be same direction. Only can generate work. You have two mathematics equation here. One equation give you three-dimensional ijk. One equation give you j direction. Recall back what is work direction or work definition. Work equal to force times displacement. This is a displacement. This is work. When you take this one, multiply by this one, or W dot dr, right? Just now it's force, right? Now you change the force to W. W dot dr. How do you multiplication with the vector unit? I multiply by j, what do you get? I dot j, 0. I dot j, what does it mean? One go this way, one go this way, perpendicular. You know that dot products, I dot j, you get 0. Just now the cos theta, you still remember just now? Why 90 degree you get 0? Because cos theta 90, you get 0. This one also fall under appendix B. Yeah? If I'm not sure what I'm talking about, go to appendix B and read. Okay. So basically, you take this one multiply by this one. So Wj multiply by this one. Wj multiplied by this one, Wj multiplied by this one. Okay, so basically this equation, because why you use this set equation? Because this one move in the pathway that is not straight line. We use this integration equation. So basically you are doing this multiplication that I do just now. W multiplied by this one, W multiplied by this one, W multiplied by this one. And recall dot product, I multiplied by J, you get 0. J multiplied by J means J dot J, you get 1. K multiply K dot J or K multiplied by J, you get 0. So the only remaining in this mathematics model here is W dy with a negative sign. Okay, the product of this vector equation here, you arrive at minus W dy. And you change the limit of your integration because you only left out dy. So you integrate from y1 to y2 for gravitational force. Or weight, we call it weight. It's a negative sign. You integrate from y1 to y2. With this, arrive at the equation that you're very familiar with. It is your m, w is mg. Y2 minus y1 is your h, which is equal to your mgh that you learned in your physics, which is gravitational work done by the gravity. Okay, so from here we derive the equation for the work done by the weight equal to negative W y2 minus y1. Okay, of course you can rewrite this equation into a positive form. You can write W bracket y1 W W equal to y1 minus y2. Okay, you can rewrite the equation into a positive form if you want. So I pull this equation up. So this is the second equation for today, important one, because the previous section is talk about force. Now we talk about weight. So this equation give you when you have a effect of weight, when there's no additional force acting on it. This is purely gravitational force. Okay, W mg. You get this equation. So this is purely gravitational force, which is our weight. The previous one is a force. So in the real tutorial question later on, you look at the scenario, you combine these two effects together. So later your equation might be very long because you consider weight, you consider force. Then you have a loss of energy work to do. So you arrive at this equation. Work equal to minus W and the change of your elevation, your Y elevation, your Y elevation. Okay, this diagram it use Y, but if the diagram give you Z is the vertical axis along with the gravity, then this is dz, delta Z. So you have to be clear of the equation here. Why this one? Why? Because our vertical axis is Y. So if other textbook they use Z, don't confuse. You have to know that work always looking at the force and the direction of the displacement. In this case, is your work. All right, is your weight. So your weight is doing work using this equation minus W delta Y. Okay. What else? Okay, so this statement is just tell you why there's a negative sign there. Why there's a negative sign there? Because your work and your displacement is different. Because your delta y, you calculate positive to where? Your y-axis is going up positive. Huh? And your work is going down, you get negative. Huh? Still back to the previous concept you learned. When did your force give you positive value? When your force and displacement going same direction, or angle from 0 to almost 90 degree, you get positive direction, meaning these two going same direction. When two of your object here, either force or displacement, go different direction. If your force is opposite direction, force is going this direction, displacement going this direction, you get a negative work. Same with this one. Because your force is going here, displacement is going there. You get a negative sign over here. Okay, then this is just an add-on question just to ponder for today. So, however, if the particle displays downward negative y, the work of the weight is positive y. Okay, try to think about it, right? But basically, I already explained the answer just now. Okay. Okay, I think we stop here. Let me end the recording.